Our second to last speaker is Sarfaraz Hussein. He's an applied scientist at Amazon, and he used to be lead data scientist at the Home Depot. He was at Symantec. He has a PhD and a Master of Science in Computer Science from University of Central Florida. And I asked him, because he's got a very scientific kind of background, what term really represents him. And he said, you know how there's kind of like a good witch and a bad witch? Instead of a bad scientist or evil scientist, he's a good scientist. So please welcome Sarfaraz.
Hello, can you hear me? Cool. Thank you everyone for bearing with me in the final part of this presentation today. The title of my presentation is Needle in a Haystack, Outlier and Novelty Detection. So this would be the agenda for today's talk, a few minutes which we have together. We'll define the problem, what the problem we are going to talk about, the significance and the causes of the outliers in a data. What potential applications can we apply outlier detection and novelty detection to? What are some state-of-the-art techniques for outlier detection that are available in the literature and machine learning? Then we actually discuss a different topic, but slightly related, is the out-of-distribution detection. Out of distribution, I will explain what it is and how it is related to the problem of outlier detection. And then finally, we'll discuss this year's recent paper, which we have, a case study in healthcare related to the out of distribution detection. A very interesting work I'm going to talk about, and we'll end with a conclusion. Let's start with the game. So I'll show you an image. It is an image of a CT scan. And what you have to do is, whenever you see an animal in that image, you need to clap your hand once like this. So are you ready? Okay, let's see. An animal in this image. Okay, we get a few claps. So if you see, unfortunately there isn't a pointer, but if you closely see on the top right, you will see an angry gorilla in this image. So this is a CT scan. An experiment was done, and this image was shown to multiple radiologists. And what they do, they generally scan for cancers in the CT scans. So that what they were told is, just find lung nodules, lung cancer in these images. And they found that about 83% of the radiologists were not able to detect this angry gorilla, which is staring right in their faces. And the reason being is we actually suffer from inattentional blindness. What we are looking for, we generally find that. And what we are actually not looking for, we don't actually look for it, and we don't ultimately find it. So that is the problem, that once you have humongous amount of data and a person is actually working in a dark room day in and day out, then they are actually tuned to find regularities or lung nodules which they are actually prone to look for, and they miss these type of cases. So what are these outliers? Outliers are generally objects that are different from most other objects. There is a field in statistics where we generally find these outliers from the data and then remove it, and then we train an algorithm in order to train a classifier. There are numerous fields in which the outlier detection, novelty detection, anomaly detection is a very important problem. And the success of many of those industries depend on how you accurately can detect these outliers in the data. They are actually rare events, but very significant. For example, a cancer, which is just one case in maybe 1 million, for example, is very important. And if you miss it, that would be a problem. And so many other examples which we are going to talk about in the next few minutes. So if you have a set of data points, you fit a hypothesis, and then what happens? You generally have outliers. But all the points which you have in your data generally pass through your hypothesis line. And that, as the name implies, outlier. Now there are two problems which are similar. One is the novelty detection and anomaly detection. And then we have another problem which is out of distribution detection. And this image actually explains these three problems very well. So once we talk about novelty detection, what happens is you are talking about a class of animals, such as dogs, which is what your class looking for and find in the data. And then there are some breeds of dogs, images of some breeds of dogs, which are not found in the data. So that would be the novel unseen class. They can be like very minutely different, but it is a different class, for example. And then there are some outliers that are nothing to do with dogs. That can be cats, horses, tigers, and so on. And then we talk about out-of-distribution detection in a data. You have a single data set which you are actually training a classifier on, for example, CFAR 10, ImageNet, and so on. And there are some out-of-distribution data sets which are entirely different from the data set which you have at hand. So how you can actually detect these out-of-distribution samples automatically using machine learning, that's what we are actually looking for. What are the causes for outliers? It can be built in the data. The underlying cause is present within the data itself. It can be because of the natural variation. There are tails on the Gaussian distribution which you are actually missing. It can also come from the way you are measuring data. So data measurements and collection can also lead to errors, and those errors can actually lead to outliers. What are the structure of outliers? A few of those structures of outliers are the point outliers, contextual outliers, and collective outliers. We are briefly discussing each of them. So what is a point outlier? A point outlier, as you can see in this image, is an individual isolated data point that is anomalous or outlier with respect to the rest of the data. So if you see here, N1 and N2 are two data collection or data clusters. And then you have O1, O2, and O3 are three set of outliers. O1 and O2 has a single point. O3 has, for example, 5 points. And if you define that an outlier should have a specific number of examples in that particular group, O3 would be as an outlier. And there are numerous ways in which you can define a cluster to be an outlier. It can be either distance-based, it can be density-based, and so on. Then there are contextual outliers. An individual data is anomalous with respect to a larger context in which you are actually considering that point. And it requires a notion of context. In isolation, you cannot identify whether this single instance or data point is an outlier or not. And these are known as conditional anomalies. And as you can see in this image, an anomaly, if a temperature drops very low in the month of June, that would serve as an anomaly. I don't think going to happen in Atlanta, at least. Then we have collective outliers. A collective outliers is a collection of related data points, and once they are collected together, then it would serve as an outlier. Again, context is important, and the collection themselves is important. And these are very important for sequential data, spatial data, graphical data, and so on. So they are not anomalous on their own. The context and the collectivity of them makes them anomalous or the otherwise. Now let's talk about some interesting applications of anomaly detection. So I worked in e-commerce, healthcare, cybersecurity. In each of those fields, you find applications of anomaly detection. So it can be network intrusion, insurance or credit card fraud detection, medical diagnosis, industrial damage detection, image processing and video surveillance, and topic detection and text mining can be some potential applications where you can use anomaly detection. So let's sprinkle some little machine learning and try to solve this problem of outlier detection and novelty detection using machine learning approaches. So the first thing, using deep learning, if we generally talk about that, the first approach that comes to our mind is an autoencoder based approach. What an autoencoder does, it tries to reconstruct the input. And what it does, it is being trained in a manner that you minimize the error between the input and the output, because you're reconstructing back your input. So what happens is you can detect the anomalies by checking the magnitude of the reconstruction error. If it is very high, you would consider that to be an anomalous data point. If it is low, then you think that this is coming from the same distribution of the data on which autoencoder is being trained on. Advantages, it's a simpler technique. The disadvantages, if there are some infrequent outliers being present in the data, that would potentially be missed. Secondly, we are training an autoencoder for reconstruction purposes. not for the purpose of detecting outlier. So when that problem happens, it is not being optimally suited for detection of outliers. The second is generative adversarial networks, or GANs. And we can use them for the purpose of outlier detection as well. And just to summarize, most of you may know a GAN has two components, a generator and a discriminator. What generator does, it actually takes a noise vector and tries to construct something meaningful out of it. And the goal for the discriminator is to tell and discern the difference between a a fake data and the real data. So that's what they actually play a min-max game, and at an optimal point, a discriminator is totally confused. It cannot tell whether the point which you have is coming from the data itself or it is a fake data point. And in machine learning terms, what it does, it turns to learn the latent feature representation from the input data which you have, the distribution of the input data which you have at hand. And then you can use it for anomaly detection as well. How? You can compute the residual, the error. It can be a reconstruction error, for instance, or it can be an error between the generated data and the real input data. And if the distance or the residual is high, it means it is anomalous. If it is low, it means it is coming from the same data distribution. So as you can see in this image, there's a random noise and the generator and a discriminator, and the goal for the discriminator is to discriminate between the real and the fake examples. For anomaly detection, there are some variants of GAN which are being used. One is ANOGAN, or anomalous GAN, or anomaly GAN. It is based on an assumption that the normal data instance can be better generated by a GAN as compared to the abnormal instances. So that's the underlying assumption on which this ANOGAN works on. And what happens is, whenever you are given a data point X, you try to search for an instance Z in the learned latent feature space which you have. And once you find that instance, you find the reconstruction error or a residual error. And based on the residual error, you can decide whether that particular instance is anomalous or not. And if you have, and again, as I said, the latent space is enforced to capture the underlying distribution of the training data, so that can help us in identifying whether a specific point is anomalous or not. At the bottom, you can see an example how you train that ANOGAN. It is an OCT, ophthalmology images, eye scans. Start with that, get the healthy data, train the model, and when the unseen data comes, pass it through the model and get the anomalies by calculating the distance or the difference between the real image and the generated image. Then, one issue with the ANOGAN is the computational inefficiency, because you have to search through that latent space. And that is being addressed by efficient GAN-based anomaly detection and GANomaly research. And what it does is, it has an additional encoder-decoder representation. And that works in tandem with your GAN. And these together can identify and work in searching for that latent representation of the data. And GANomaly, again, has an encoder-decoder network and has an extra loss that can account for the lost context, which you are actually missing in the original ANOGAN work. So if you use generative adversarial networks for outlier detection, what can happen is GANs have very good capability of generating the data. Image data, they have actually shown themselves to be working great. Detection of abnormal instances, it is actually very intuitive. There are a large number of GAN-based research work which you can actually adapt to and apply to your work of anomaly detection, and you can directly do some sort of anomaly detection. So that's a big advantage. The disadvantage, as you know, GANs have numerous problems. They may not converge. They have a problem of mode collapse. Another thing which is also common in autoencoder-based approaches is the objective function is not meant for anomaly detection. It is actually being trained for generating the data or unseen data. So in this particular instance, GAN may or may not work, although they have actually shown to be work pretty well in numerous applications. So let's talk about the problem of out-of-distribution detection. So what happens is you want to detect an out of distribution data. So in distribution is something where your training data is coming from. And out of distribution is data something which is outside. Ideally speaking, in a utopian world, what you want to do is a classifier can tell you confidently about a cat, because that is found in the data set, and can say that I'm not very sure whether this image is of cat or not. Okay? However, what happens is a classifier can pretty confidently tell you that this image is of a cat, but if you show the image of a tiger or cheetah, it will say, I'm pretty sure it's a dog. So it's wrong in the first place, and it's supremely confident about its prediction. So that's an issue which we want to address. So this is our work, which is recently came out and published, an out of distribution detection for skin and malaria images. So these are very two important healthcare use cases, and we actually work on identifying out of distribution data set in these two healthcare cases. So our contribution in this work, we do not require the network to be trained from scratch. We can actually build upon an existing trained network. We do not have any specific set of hyperparameters which you want to optimize. We actually generate out of distribution samples in a very smart manner. So if you realize an out of distribution can be anything. If you have images of skin cancer, out of distribution can be images of car, cat, dog, anything in the world other than images of skin cancer. So it's a very challenging and difficult problem how you can actually train for something which is other than what the data set which you have. We do not have any access to real out of distribution data during the training process, and we actually use the k reciprocal neighbors rather than the k nearest neighbors for the optimization and calculation, distance calculation purposes. So this is the flow chart if you can see. So once you have an anchor ID, which is an image of a skin cancer, a positives, and then you have a positive ID which is coming from the same class of examples. And then you have negative ID, which is coming from skin cancer, but different types of skin cancer. So those would be the negative examples or negative instances. And then we come up with an out of distribution surrogates. The way we actually generate these out of distribution surrogates is we pick up any image of a skin cancer, we apply grad cam or hide cam to actually find the discriminative regions in that particular image, and then we actually remove those by copying the images patches which are healthy from the image, same image, and paste it there. So now we do not have any case of skin cancer in that particular image. If you can see, the OOD surrogate which we generated is actually clean from skin cancer, and that serves as a surrogate for out of distribution. And then we have tuplet loss, which I'm going to explain. That is actually based on anchor positive examples, all the negative examples, anchor positive examples, and out of distribution examples. And then finally, we need to have a classification loss as well, because we need to actually find these classes, and that's our goal as well. So as I mentioned, before passing the image through the CNN, we actually apply hide cam or grad cam, find the discriminative regions, remove them, make the image clean, and then follow the process. And we follow this tuplet loss in multiple stages for both positive and surrogate examples. For generating the examples for malaria, what we did, because for malaria detection, the images which we have, the sequence of patches is very important. So we randomly permutated those sequences so that actually serves as a surrogate that is coming from the same data, the out of distribution data. And what is a tuplet loss? It can be seen as an extension to triplet loss, as you have already used it in many examples perhaps. Here, we do not have a single negative example. So generally what you have is an anchor, a single positive example, and a single negative examples. What we have here is an anchor, a positive example, and a series of negative examples that can serve for us to actually train that network. And since we have multiple negative examples, it actually makes sense to actually provide them weights based on their distance from the anchor. So these negative examples are actually weighted. And this is the final loss. And as you can see, we have a scaling factor that can serve to provide weights for those negative examples. C is the number of classes at hand, which you have, and A is the anchor, P is the positive example coming from the same class, and then N are the samples from the other classes. It can be negative classes, it can be the OOD surrogates which we have. And this, as you can see, if we generally use a pre-trained network, run these images through it, and then do TSNE, T-stochastic neighborhood embedding, and do the clustering. So if you can see, you will not find a very nice separation of classes here. So if you see in this image on the left, the OOD samples and in distribution samples, ID is in distribution, these are actually seem to be present within the cluster. They may be a bit further away, but they're in the same cluster. So if you see ID samples and OOD samples are present both in red cluster as well as the purple cluster. However, if we train it with the tuplet loss, the one I discussed in the last slide, you can see a very nice separation of in distribution and out of distribution examples. So if you see in distribution is all within that cluster, and out of distribution are actually very further away, some isolated points, which you can actually very easily visually vet out and see these are actually the outliers and out of distribution. However, in the previous case, you cannot actually discern the difference between in distribution and out of distribution after doing the clustering. And these are some examples of out of distribution samples which we generated. On the top, you can see the images of skin cancer. And as I mentioned, it goes through the process of class activation maps and remove those discriminative regions. And then at the bottom are the malaria images. And those are actually being permutated to serve as the out of distribution examples. And these are the results. So we have numerous data sets which we evaluated against. So derm skin is the skin cancer data set. It is coming from ISIC 2019 data set. It comprises of around 25,000 images of 8 classes of skin cancer. Clinical is also a subset of skin cancer images. ImageNet is a 3,000 image subset coming from the ImageNet data set. B-box is what we do is we actually place a bounding box, a black bounding box on the cancer itself. B-box 70 is once we actually put a bounding box that hides 70% of the cancerous region. So that actually also serves as an out of distribution. That was the synthetic experiment which we want to try. And then NCT is a colorectal image classification data set. And then there is an average of supervised and unsupervised based approaches. And as you can see with the proposed approach, which is the extreme right, outperforms the other state-of-the-art approaches for outlier detection for these use cases. And we use true negative rate at a true positive rate of 95%. So if we fix the true positive rate of 95%, what is our true negative rate? Which is a detection of these out of distribution samples. And we also did, so what we did, another thing which we did was we actually consider 7, for example, we have 8 classes, we consider 7 classes to be in distribution and consider the 8th class to be out of distribution and repeated that experiment multiple times so that we have more data or more results associated with the same data set itself rather than actually considering one data set to be in distribution and the others to be out of distribution. You can refer to the paper for more details. And these are the images, the results for the malaria data set. And as you can see, the RBC healthy is the malaria data set itself. The coin fusion is the fusion of coin images with these malaria images. Flag fusion, we consider flags of about 192 countries and fuse them with these malaria images just to actually make it out of distribution. And that is a fairly common practice for this specific data set. And then again, we have ImageNet, 3,000 samples, randomly sampled. NCT is a colorectal image data set. And then we have the second last and last row are actually the average for the supervised and unsupervised approaches. And here, as you can see, we do pretty well for RBC For the rest, the Mahalanobis, which is another approach, performs relatively better, but in the end, the true negative rate at a TPR of 95%, we actually outperform the rest. And this is actually another visual way of the histograms. And if you can see the OOD score, so the blue is in distribution, the orange is out of distribution, and you can see a very nice separation of histograms, the scores, when you consider each of those data sets, which is NCT, ImageNet, dermoscopy. There is a bit of an overlap in the clinical data set, which is again the images of skin cancer. And then BBOX 70 and BBOX are also pretty well. And to conclude, I would say these problems of outlier, novelty, and out-of-distribution detection are a very exciting area of research. The applications, as I mentioned, are very wide-ranging. If any of you are interested in this research area, for any application, as I mentioned, the applications cannot be necessarily medical imaging, but the others as well. So feel free to reach out to me via email or LinkedIn. I'll take any questions. Thank you.
Any questions?
Hello. It's a great talk, Sarfaraz.
Thank you.
I'm coming from manufacturing industry where the scrap rates are pretty low and outlier detection is a very common problem. So what kind of techniques do you see from your experience work well in that kind of data sets and that kind of scenarios?
Sorry, what problem did you explain? I didn't get it.
I'm coming from manufacturing kind of.
Manufacturing.
Manufacturing typically.
The data set are images or?
A mixture of images, or it can be like product features coming out of it, like end-of-line scraps. That's what we are trying to predict. Like
yeah, good point. I think one thing which I did not focus that much was the feature themselves. The feature extraction. Here we are assuming a pre-trained network against which we extract the features and then do the outlier detection process. For images, I think the approaches which I mentioned, based both the autoencoder based and GAN based, should work decent in those situations if there's images, because there's autoencoders and both GANs are found to be performing quite well for image scenarios. So for that, image generations and image based approach, it should work pretty well for finding the anomalies. However, for the other types of data, structured data and those sorts of things, it depends on how you extract the features. So if your features are very discriminative enough, as long as the context, and there is like a lot of NLP stuff which other people talked about in today's talk. So if you extract any of those like word-to-vec or bird types of features, the transformer-based features, and then do any sort of these techniques, maybe as simple as maybe autoencoder, that can actually give you good performance there as well. Cool. Thanks.
Cool. All right.
Thank you.